We're going to figure out whether there are any points of inflection. For this particular function. And again, in the interest of time here, I'm just going to tell you what our second derivative works out to, and I'm going to encourage you to go through the calculation and actually check that. So f double prime of x, if we apply the quotient rule again from our first derivative, we will get a second derivative of 8x plus 16 over x plus 2 to the fourth. So that's what you would get after a little bit of simplifying and using the quotient rule. Now, if this is the answer that you came up with, there is a little bit more simplifying we can do here. You might notice you could factor an 8 out of the numerator. That would leave you with a factor of x plus 2. And in fact, we can cancel a factor of x plus 2 from the numerator and the denominator. And so our fully simplified answer for f double prime of x would look like 8 over x plus 2 all cubed. So I'm going to write here, check this. And I would really encourage you to pause the video and just make sure that you can get this formula for f double prime of x and that you can get it simplified. So to figure out whether we have any points of inflection, we need to look at the critical points here. We're looking for any places where f double prime of x can change sign. So that can happen when f double prime of x is 0 or undefined. And again, I'm going to underline this because when we were dealing with polynomials, we automatically just set f double prime of x equal to 0. That was because polynomials are never undefined, so we never needed to worry about that. But now that we're working with rational functions, we really need to think, where can the numerator equal 0 and where can the denominator equal 0? Or in other words, where is this second derivative here undefined? Those are the places where possibly f double prime of x can change sign. Okay, well, if we take our numerator, set it equal to 0, ain't gonna happen, so there's no x values there. But taking our denominator, setting that equal to 0, x plus 2 cubed is equal to 0 when x plus 2 is equal to 0, so when x is equal to -2. Okay, so underneath here I'm just going to write no solution, no x values for that particular situation. Looks a little bit weird to just write 8 equals 0, but we can write under there no solution. So no x values from the numerator equaling 0, and our only critical point then is just x equal -2. So let's draw our number line here. Okay, we're going to think about what the signs of f double prime of x are on each of these two little intervals here. And then we can write down what that means for our function. So choosing an x value in the first interval, you might go for maybe -3. Plug that into our second derivative. It's going to come out negative. And again, because -2 is the only place where f double prime can change signs, we know that the sign of f double prime of x does not change anywhere on that interval. So just testing that single point tells us the sign of f double prime in that entire interval. Okay, maybe over here we might try, say, plugging in -1 or 0. I like 0, so plug 0 into f double prime. We get a positive number. All right, so what this tells us about our function, a negative second derivative means that our function is concave down, so it looks like an upside down bowl. Over in the second interval, function is concave up, so it looks like a right side up bowl there. So that will help us when we're making our sketch. So to answer the question of whether there are any points of inflection, well, a point of inflection is a point where the concavity changes. So initially it might look like we've got a point of inflection at -2. So we could go back to our function and figure out what the y value is there. Remember, when we're sketching a graph, we're always interested in the y value coming from the original function. So we want to go look at f of -2. And if we think back to what our function looks like, just remind you what it was. F of x was x squared over x plus 2. Unfortunately, when we go and plug -2 in here, it's undefined. So in fact, there is no point of inflection. So that was a little bit of a tricky one. Initially, it looks like there's going to be a point of inflection, but when we really check it, it turns out that the function is not defined there. So I'm just going to cross off this. It doesn't turn out to be a point of inflection, and there's no point of inflection for this particular function. So now we can go on to the very last part of the question. We are going to sketch our function. So remember, our function looks like f of x is x squared over x plus 2. All right, so I'm going to make a nice big sketch here. We'll give ourselves lots of room. And we can think about what kinds of values we're going to need to be plotting here. Well, if we think back to the points that we found, we did find a relative maximum that had x value -4. So we're at least going to want that x value to appear on our graph. The y coordinate there was -8. So I'll make room to plot that point. Okay. Some other points that we were interested in, well, we had an intercept of 0, 0. So 0, 0 is going to be on our graph. -4, -8 is going to be on our graph. And we didn't have any points of inflection. So in fact, these 2 points here are the only points that are going to come up when we start to sketch our graph. Something else that's going to be really helpful for us is the asymptotes that we found in this question. So if we look back to earlier in the question, we did find a vertical asymptote for this function. It was at x equal -2. So I'm just going to draw in a dashed line there corresponding to our asymptote. Okay, I'm going to label that just up at the top so it's out of the way. So x equal -2. And we also found a slant asymptote in this particular problem. We had a slant asymptote of y equals x. So we could throw on a few more points here. Those might help us with plotting our line. So y equals x, just a line that's coming up just like that, and it's going to be going down over here as well. Try to make that look roughly straight. Okay, so there's our slant asymptote, y equals x, and we'll label that as well. So we can label our axes now. We can indicate a little bit of scale. So we got scale indicated on the y-axis and on the x-axis as well. I think I'll do it under the x-axis just to keep it out of the way. Okay, and we got our 2 points on there. So now we need to just start thinking about the shape of the graph. Well, if we look back at when we were looking at a relative max and relative min points, what we said was that our function was increasing from x values -infinity on up to the x value -4. So our function was coming up to this point here, and then it started to decrease. So we've kind of got the shape of an upside down V there. And I'll just leave this on here for a minute until we're really ready to think about the concavity. Okay, over on the other side of the vertical asymptote, we said that our function was again decreasing to the right of -2, it's going to be decreasing all the way down to the origin until x equals 0, and then it's going to start increasing again. So what that means is that we've got sort of this upside down V shape on the left side of the vertical asymptote, and on the right side of the vertical asymptote we're going to have something like a V shape. So now we need to look at the concave up, concave down behavior and really just fine-tune our sketch. Okay, so I'm going to erase these little dotted lines here. We know we've got an upside down V of some description, and let's think about our concavity. We said that the function was concave down for x values that were less than -2. So our graph is going to have this sort of a shape. It's going to look like an upside down bowl. We've got a relative maximum here at this point, but we also need to draw it so that our function gets close to these two asymptotes that we've got on here. So we really want to represent the fact that as x gets close to -infinity, our graph is getting very close to this line here. So it's really showing this kind of behavior. It's coming up slowly here, coming up to a relative maximum, and then it's going to decrease and it's going to get close to this vertical asymptote here. So we have this kind of behavior. Okay, so I'm just going to erase our earlier attempt there because we've now fine-tuned that, and we're really showing that our graph is approaching these two asymptotes there. Okay, there's our relative maximum. We can label its coordinate there now at -4, -8. All right, so now for the right-hand side of the graph, we know we're going to have something like a right side up V shape, and from our concavity, we know that our function is concave up when x is bigger than -2. So we're really going to have something like a U shape here. It's going to be close to the vertical asymptote, coming down to the origin. The origin is a relative minimum here, and then our graph is going to start to come back up. Now, often this is a situation that students will find tricky because we don't need to worry about this slant asymptote near the origin. Okay, so right around here we can ignore it. All we know is that as x gets really big, as x gets close to infinity, our graph is going to get really close to this line here. Whether it's just above the line or just below the line, we might need to think about that a little bit. So if you're ever in doubt here, you could always plot another point. So you could, for example, think about when x is equal to 1, what would our y value be in our function? So if we plug x equal 1 in here, we'd have 1/3. Okay, well that will actually go a long way to help us figure out the behavior here. It tells us that right here we got this point on our graph. So as you might suspect, our graph is coming in below the slant asymptote. It's kind of slowly growing like that, and as x gets bigger, it's going to get closer and closer to this line here. Not actually touching that line, but just getting very close to it. Okay, and if you're still in doubt about this behavior, feel free to plot a few more points. You could say plug in the x value 2, for example, and just keep getting a little bit more information. So let's label the point 0, 0, because that was a relative minimum and it was one of the intercepts that we found. And now we can just check our sketch and make sure that it's got all the features that we want. So it's got all the points that we found labeled. It's got all the asymptotes that we found are labeled here. We've got our axes labeled, and we've indicated scale on both of our two axes so that we know what each tick here corresponds to. So we are done our sketch.